Hi there. Welcome to the loop compensation of a multiple output flyback using Jack's model. This model is one that was introduced to me by Jack Alexander, and the other three videos I talked about how he implemented. And I got an email by one of the viewers that, well, how do you use this to simulate multiple outputs? So a very valid question. So right here, here's the schematic. I show a schematic of a flyback, and this flyback, it's 12 volts at half an amp, which is one of the primaries. And so you have the one of the secondaries. So you have a primary here, right here, LP, and we have L secondary 1, and then I put L secondary 2 here. So that's the L3. And I'm using the coupled inductor model, which is a K. And when I use a K, I have to define which inductors are coupled. So in this case, I have L1, L2, L3, which is L1, L2, L3. Now, in this case, I'm closing right here is my output node. That output node is actually connected right there. These are my sampling resistors. Sampling. Okay, and that goes as part of the feedback, and it goes into your PWM. And this one's the current mode PWM by Basso, which is a switching model. So this calculates the voltages and currents, very much what you would see if you were to breadboard it. You would be able to plot the schematic and actually get the waveforms very similar to what you get on the breadboard. Now, here I'm using a parameter. I defined it NR. So basically, the secondary is dependent on whatever your primary is, and it's dependent by the turns ratio squared. So what I did is it's NR times NR, which is NR squared times the value of LP. And I defined it for the primary, for the secondary, for the 12 volts, I defined it here. So I have a turns ratio of 0.5. Then on the second secondary, and I forgot to mention that this is 24 volts at 1 amp. Okay, and I use the same method here to define it. NR1 times NR1 times LP, and I use this parameter to define the turns ratio. So basically this one has a turns ratio of 1 to 1 in respect to the primary, and this one has a half, or 0.1 to 1 when reference to the primary. Okay, so in this case, the loop is closed on this one. Okay, so since it's closed on the 12 volts, any capacitors that are connected in the second secondary of the 12 volt line has to be reflected back, and you actually put these in parallel with everything else. Basically, you're going to have something like this. But this is this, and it's reflected through the turns ratio. Now you can use Spice, or actually you can use the model that Jack did, but I'm just going to go ahead and do a little bit analytically, use some of the numbers. Here's a simplified schematic. The turns ratio, like I mentioned, is 1 turn at the primary. The first secondary is 0.5. Okay. Now, just keep in mind the 0.5 is not a real turns ratio. It's just a ratio, but it's not a real world. You would have to scale it up where you would have a multiple. Okay, and of course it's a 1-to-1 ratio. Now, when you're gonna reflect, you since this is the one that is being closed, you want to reflect this back to uh, uh, this node, okay? Because this node is where I'm closing it, and that's where the feedback resistors are connected. So in this case, what we have to do is we need to find the equivalent uh, resistance, or at least the total. In this case, I want to find, or I want to translate this RL2 to the first secondary, and that is done here. I call this the reflected, okay, and it's RL2. In this case, I get the turns ratio of this, of the first primary, of the first secondary, divided by the second secondary squared, so I end up with 6 ohms. Okay, and we know that the equivalent, now that we know that there's a 6 ohm, which is the reflected, okay, you know that these two are in parallel. Sorry. Okay. So that's what this is. So you have a load equivalent of 4.8. Okay. Second, now we find the equivalent capacitors. In this case, we want to look at C2. So, okay, we want to translate this C2, bring it up to this node, and that is done basically the same thing, except that since it's a capacitor, we flipped the turns ratio, and the resistor we had 0.5 divided by 1 turn squared. Well, for capacitors, you invert it, you flip them. So basically, what it does, it amplifies or actually multiplies your capacitance. In this case, this capacitor was, let's go look again, it's 47 micro, 47 micro, and when you go through the reflected turns ratio, you end up 188 microfarad. Okay. So C1, which is the closed capacitor, is 4.7. Okay, and it's in parallel with C2 reflected, so we end up with the total capacitance of 192 microfarads. So now that we have the, basically, we want to get actually this. We want the RL equivalent, CO equivalent, and RSR equivalent. Okay. Well, we are in position to calculate that. This will give you a whole. Okay, and that's calculated by this, which is 1 divided by 2 pi, which times the equivalent capacitance times the equivalent load. So you end up with 172 hertz. Okay, and we also do the same thing with the ESR. Get the ESR of the secondary. Go through the same turns ratio, and I end up with a 3.75 milliohms. Okay, that's in parallel with the first. Okay, so I end up with the equivalent of 3 milliohms. Okay, and now you know what this is. It's 3 milliohms. Okay, and this will give you a 0 in combination with the output capacitance. So when you do the calculations, you end up with 276 kilohertz, and that should be a 0. So got that. Okay. So I chose. You don't have to. I chose to put a transformer here, just so it will look a little bit more intuitive. Typically, I don't put a transformer here. I typically just put the connection here, okay, and this I connect a second transformer, ideal transformer, and I connect it to that node. But just to make it a little bit more easier to see or visualize, I went ahead and put a transformer here, okay. And I guess the important that concept that I want to show is that when you put the transformer here, be sure you put the turns ratio, which is the secondary divided by the primary, okay, and this would be for the 12 volts. And then I put a second transformer, and then the turns ratio of that was 1 to 1, okay, so that's the second. And of course I have my output filter here, and I have my output filter here, okay. Now the thing, once you do this, then you need to set the gain of your voltage control current source. And basically, since you're going to have one half an amp coming in through here, that reflected to the primary means that you're going to have 250 amps that will be supplied by this current source. Okay? But not only is that supplying the 250 milliamps to this source, it has to supply that current down to this direction. So in this case, you have 1 amp that has to be supplied. Okay, since you have a turns ratio, then it's pretty straightforward that you're also going to have 1 amp here. So basically, it's going to be the 250 plus the 1 amp. So you're going to end up with 1.25 amps that is supplied or actually flowing through here. Okay. Now, Jack's rule was that he always wanted a 1 volt here. Okay. So to set the gain is 1 volt times the gain, and I'm going to call this GM, and in this case we set it to 1.25. That way when we multiply times 1.25, we'll get 1.25 amps coming out from this. So that's the way you set the gain. That way it will ensure that when the DC operating point is calculated, you end up with 1 volt at this node. And you'll see in the simulation that it works out fairly well. Okay, so let's go ahead and simulate. Okay. Here's the AC model using Jack's model. And one of the things that I like to do is I have the venable, what I call the venable resistor in AC stimulus, and I define this as out. And now this out node is actually this out. So just to make it a little bit more intuitive, I'll set it right here, which is the output. And this input, I'll leave it here because this combination of the out and in actually gives you the system, the total system loop. Now I went ahead. I'd like to also name a second variable, which is I in or n1, and when I define it here, I defined it as this output divided by this input, in1. That will be uh, our power plot, which is named here. So in this case, I'm going to have a total system loop response and then the response of the filter. And that basically what I'm trying to get at is I want to see whether it matches with my calculations. Okay, so I'll go ahead and run the Bodhi plot from 1 to 100 meg, 100 decades. I'll go ahead and run. Okay, I'm gonna go ahead and see if this shows up a little bit better. This may look a little bit better. I'm gonna go ahead. Oh, let me backtrack. This is the total loop response, and this is the response of the output filter. Let me go ahead and turn this off so we can concentrate a little bit more on the output filter. So this is the output filter. So according to the calculations that I did here, I should have a pole at about 172. Okay, so I can go ahead and put a plot, and the 0 is somewhere in here. You can actually put a second cursor and then look for the negative 3 dB, and I can do that. And negative 3 dB is right there. And if you look in here, it says 173. Let's see, what did I calculate? 172. So it matches fairly well. Okay, and then the 0 of the output loop is somewhere. This is a little bit. It's not as exact, but somewhere from here to here. Now if I look in here, probably be close to. So that's 200, 208. You could possibly put it here, 281. So it's in the ballpark. So this calculation that I did up here actually does coincide or matches what Spice says. So now, going back, I'm going to go ahead and resimulate this. Okay. As you can tell by this line, being that it's straight, this tells me that I've already compensated. And basically, I take the time constant, of this pole. Once I get the time constant, divided by 5K, and I should get the value of this capacitor. Okay. Then I do the same thing. I get the time constant of the 0 divided by 5K, and I get the value of this, the roll-off capacitor. So once you set them and match them, you have a beautiful loop response. Question is it a valid, or how close to it to actual operating conditions? Will it does it match real world, or at least a simulation using, let's say, a transient or a switching model? Okay, uh, what I can do is I can hook up a 40 ohm resistor here, and I can switch it on and off, basically do a step response or load dynamic loading. And for this, I'll go ahead and do a transient analysis. As it's doing the transient analysis, it's switching on and off, and how fast it recovers is determined directly by your bandwidth of your error amp. So if the band or the transient or the dynamic loading of the AC model matches the switching model, then you can have fairly good confidence that they're a match and that the model is valid. Okay. So here's the transient or dynamic loading using Jack's model. Okay, so it goes up and down, and now we can go ahead. I can use this model, which is the bustle model. I did the same thing. I put the 40 ohm. I'm switching it on and off, and I believe I already did the simulation. Actually, it takes a while since it's a switching model. It takes time for it to uh, make the calculations and then plot it. As you can tell, it takes a bit of time to load up the data. So now what I'm going to do once it loads up, what I want to do is I'm going to open up Jack's data, and I'm going to lay them on top of each other and see if they match. As soon as I turned off the recorder, the plot came up. So basically, it's a lot of data. Let me go ahead and refresh it. Okay, this is the result of the switching model, Russell's model. And now I'm going to go ahead and open up Jack's model. Should be a profile, and it should be multiple AC. Should be this one. Clear old data. Nope. Okay. So it plotted the second one, but the plot is real thin, and this is actually the ripple, the one in yellow. So go ahead and see if I can pick it up. No. Okay. I'm going to go ahead and go to maximum. Let's see what happens. Fresh. Okay, there you go. Okay, so let me go ahead and zoom in. See if I can zoom in that part. Okay. Go to options. And here's in black. Let's see if it looks any better. Okay. White. Okay. So the red is the transient or the switching model, the output of the switching model, and the red is Jack's model. And if you follow this actually follows, or the red actually follows the top envelope. It looks pretty close. Now if you look in, if I expand, you can see there's a lot of junk in here, part of the rip. But if you would cut off that part, then you basically have a match. So this gives me very good confidence that the model that I'm using will predict what the bandwidth and dynamic loading effects will be calculated and simulated properly. Thank you for watching.